Your teacher today is Dr. Bbosa Science. Dr. Bbosa is a teacher at the Science Foundation College, the best school that teaches sciences. Today we are going to study A-level physics, lesson 11, derivation of e.m.f induced in a moving rod across a magnetic field. A. Derivation of e.m.f induced in a moving rod of electromagnetic induction. Consider a rod of length L meters moving at right angles to a uniform magnetic field of flux density B Tesla and with a uniform speed V meters per second as shown below. From the laws of electromagnetic induction, the induced e.m.f, capital E, is equal to d phi dt, but phi is equal to BA. Substituting for phi with BA, induced e.m.f E is equal to negative dBA over dt. Negative because the area is reducing, is equal to negative B dA dt. But dA dt is equal to negative LV. Substituting for dA dt with negative LV, E is equal to negative B times negative LV. Therefore, the induced e.m.f is equal to BLV. B. Derivation of e.m.f induced in a moving rod by considering the force exerted on the electrons. By virtue of motion of the rod in the magnetic field, the electrons inside the rod experience a magnetic force. Illustration. Applying Fleming's right-hand rule, the induced e.m.f for current moves from Q to P. The electrons flow or drift from P to Q. By conversion, current and the electrons flow in opposite directions. Thus, P acquires a positive charge and Q acquires a negative charge. An electric field, capital E, is thus set up which attracts electrons towards positively charged P. At equilibrium, the upward electron force is counterbalanced by the downward magnetic force. That is, capital E is equal to BeV. Cancelling out the electron charge small e, capital E is equal to BV. But E is equal to E dash over capital L, where E dash is the induced e.m.f. Substituting for electric intensity E dash over capital L is equal to BV. Therefore, the induced e.m.f. is equal to B LV, where V is the speed of the load, capital B is equal to magnetic flux density, and L the length of the load. C. Derivation of e.m.f. induced in a moving load by applying the principle of conservation of energy. Consider a load PQ placed at right angles to a magnetic field of flux density B Tesla as shown below. Suppose the load is moved through a distance of x meters in time t seconds. From the principle of conservation of energy, work done by the external agent in moving the load is what is conserved into electrical energy. Therefore, electrical energy is equal to work done in moving the load. If E is the induced e.m.f. in the load, then EIT is equal to force times distance. But force is equal to BIL. I is the induced current in the load. It implies that EIT is equal to BIL X. E is equal to BL X over T. Since X over T is equal to V, the speed of the body, then E is equal to BL V. Therefore, the formula for induced e.m.f. in a moving load across a magnetic field is BL V. Example 1. A load PQ 1.2 meters long moves at right angles to a magnetic field of field density 0.4 T at a speed of 4 meters per second. Find the e.m.f. induced in the load. Solution. The induced e.m.f. E is equal to BLV is equal to 0.4 times 1.2 times 4 equal to 1.92 volts. Example 2. In the figure above, a load PQ of 1.2 meters long is moved in a perpendicular magnetic flux of 0.4 T at a speed of 4 meters per second along frictionless railways X, Y, and W, Z. Find the power generated in the load. Applying Fleming's right-hand rule, the induced current flows from Q to P. This gives the polarity of induced e.m.f. with a positive terminal on side P. The induced e.m.f is equal to BLV is equal to 0.4 times 1.2 times 4, which is equal to 1.92 V. At the junction, I is equal to I1 plus I2. From I is equal to V over R, considering loop 1, I1 is equal to 1.92 over 3. This is equal to 0.64 amperes. Considering loop 2, I2 is equal to 1.92 over 2, which is equal to 0.96 amps. I is equal to I1 plus I2 is equal to 0.64 plus 0.96, which is equal to 1.6 amps. Power is equal to EI is equal to 1.92 times 1.6 is equal to 3.1 watts.